Hi everyone, and in this video we're going to prove that the irrational numbers are dense in the reals. One of the first facts that we learn about the way that the rational numbers sit inside the reals is that they are dense, which means that for any real number x, we can approximate with a rational number q arbitrarily well. So given any epsilon greater than 0, we can always find some rational number that is within epsilon of x. Here I've depicted this where we have some small radius epsilon and we can make it as small as we want, so that about this point x, which is real, we can always find some rational number q equals m over n, maybe for integers m and n, such that q and x are within epsilon distance of each other. Topologically, we can say that the closure of q with respect to the metric, the absolute value, is the real numbers. Now we want to show that the same is true for the irrational numbers, which I'll be denoting by r set minus q. That is, that the closure of the irrational numbers is also the real numbers. So how are we going to do this? Well, we're going to use one of my favorite theorems in topology and analysis called the bare category theorem. So it states the following, and it has many different versions, of which in this video we'll be using one specific one, but it holds in more generality than the one that I'm phrasing here. Let X be a complete metric space. This means that if we have a metric space, every Cauchy sequence converges. It's always true that every convergent sequence is Cauchy, and completeness is when we think intuitively that if points get arbitrarily close to one another, they get arbitrarily close and eventually converge to some limit that is contained within the space. So that is, they get close to some infinitesimally good degree of accuracy, to some prescribed point in that space, which is the limit. We're going to let u sub n, where n is greater than or equal to 1, consist of a countable collection of open sets in X that are dense. So for each of these u sub I in the collection over here, their topological closure is X itself. Then this qualifies X to be something called a bare space, and this holds for other spaces as well. But the important result is that the intersection of all of these open dense sets itself remains dense in X. So somehow we're going to use this fact with the real numbers and the metric topology to prove that the irrationals are dense within them. We want to express then the irrational numbers as some kind of open intersection like this. So how are we going to do that and eventually show this density? Well, one of the facts that we learn about the rationals as well, that is fundamental to basically everything in analysis, is that they are countable. That is, they can be put in bijection with the natural or counting numbers, so we can enumerate them as follows. So let r sub n greater than or equal to 1 be an enumeration of q. So this is just a countable list that consists of all of the rational numbers. And for each n, we're going to design an open set, and because the rationals are countable, we can generate countably many sets, one that corresponds to each rational number. We're going to define u sub n, which are going to be the u sub n as above, these match, is going to be the real numbers excluding just that one point, r sub n. And we're going to do this for each n, so we have this collection of sets that are going to be open because these singleton sets in any metric space are closed. Hence their complement is going to be by definition open. So we have a countable collection of open sets, and these are also dense. This is obvious because since they're open now, the closure is just the minimal closed set, or the intersection of all closed sets in the space that contain it. However, this is just the real numbers themselves, and this is obvious to realize. Okay, so now we have, for all n, the closure of u sub n is just the reals. So these are dense, which we've stated above. Okay. Well, now what? Then we consider their intersection. Well, what is their intersection going to be? Their intersection is going to be the set of all elements that lie in each and every one of these sets. Now, no rational number can be contained in each of these u sub n. This is because for each of these u sub n, there's going to be exactly one rational number that is missing. Hence, the rationals cannot be contained in the intersection of these sets. It follows that if we take the intersection across all of these u sub n, where one rational is missing from each one of them, then this is just the set of irrational numbers. And then by the bare category theorem, we've expressed the rational numbers as a countable intersection of open dense sets. Because the reals are a complete metric space, we are done. All right, thanks for watching.